Hello dear students, I'm Dr. Moin. In this video we are going to discuss about atomic absorption spectroscopy, which is also known as AAS. So here are the contents of current video. First of all, we'll see the introduction of atomic spectroscopy. What is atomic spectroscopy? Then we'll see a list of various atomizers used in this atomic spectroscopic techniques. Then we'll see the principle of absorption spectra. Then we'll see how sample is introduced into the system. We'll see flame atomizer in detail. We'll see burners, and in the end we'll see the various line sources. So let's start with atomic spectroscopy. Atomic spectroscopic methods are used for qualitative and quantitative determination of more than 70 elements. So it means that more than 70 elements, these can be detected qualitatively or quantitatively simultaneously. Typically, these methods can detect up to parts per billion, parts per million to parts per billion level, and in some cases even in smaller concentration. Means even very dilute solutions, they can be analyzed by using these atomic spectroscopic techniques. These methods are very much rapid, easier to use, and they have high selectivity. Spectroscopic determination of atomic species, it can only be performed on a gaseous medium in which the individual atoms are well separated from one another. Means if our sample is present in gaseous form, okay, that's good, but normally our sample is present in liquid form, in solution form, or it may be in solid form. So the first step will be, there will be the atomization process. And what will be done in this process? The sample will be volatilized and decomposed in such a way to produce a gas phase atoms and ions. So here is the classification of various atomic spectroscopic methods that is given here in the form of table, showing various atomization methods or atomizers, their temperature range, the type of spectroscopy, and what is the name of technique. So we'll see them one by one. So first atomizer, that is called inductively coupled plasma, ICP. Temperature range is 6000 to 8000. So this temperature range can be provided by this inductively coupled plasma. So in what type of spectroscopy it is being used? It's being used in emission spectroscopy. And the name of technique is inductively coupled plasma atomic emission spectroscopy. In short form, it is called ICP-AES. It's also being used in mass spectroscopy. So it's called inductively coupled plasma mass spectrometry, ICP-MS. Next atomizer is flame. The temperature range is 1700 to 3150 degrees centigrade. It's being used in all types, absorption, emission, fluorescence. So when it's being used in absorption spectroscopy, it's being known as atomic absorption spectroscopy, which is the topic of current video. When it's being used in emission spectroscopy, it's called atomic emission spectroscopy, AES. And when it's being used in fluorescence spectroscopy, it's known as atomic fluorescence spectroscopy, AFS. Then the next atomizer is electrothermal atomizer, and the temperature range is 1200 to 3000 degrees centigrade. So it's being used in absorption and fluorescence spectroscopy. So when used in absorption, it's called electrothermal AAS. When being used in fluorescence spectroscopy, it is called electrothermal AFS. The next atomizer is the DC plasma, direct current plasma. The temperature range is 5000 to 10,000 degrees centigrade, and it's being used in emission spectroscopy only. And the technique is called direct current plasma spectroscopy, DCP. And the last one, atomizer, is the electric arc. And the temperature range is 3000 to 8000 degrees centigrade. It's also being used in emission spectroscopy. And the type is called arc source emission spectroscopy. And now we will concentrate on our topic, and that is atomic absorption spectroscopy. So let's see the principle of absorption spectra. In atomic absorption spectroscopy, an external source of radiation impinges on the analyte vapor. So we use an external source, and that is producing radiations. So these radiations are made to fall on our sample, which is shown in the diagram A. So these are the radiations which are coming from the source being used, and here is the sample. If the source of radiation is of appropriate, if the radiations are of appropriate frequency or wavelength, it can be absorbed by the analyte atom and promote them to the excited states. So if these radiations, they have some proper wavelengths, so these may be absorbed by our sample, and sample may be excited from the ground state to the excited state. For example, if we talk about sodium, so we know that sodium has only one valence electron. So when we are using the source of sodium, so radiations are falling on the sample containing sodium. So its valence electron that is present in 3s, that might be excited towards 3p, 4p and 5p by the absorption of radiations of wavelength 285, 330 and 590 nanometer. So there will be resulting 3 absorption lines. You can see at the position of 285, 330 and 590. Means sodium has absorbed these 3 radiations of wavelength which I mentioned here. Then after a nanoseconds, because excited state is the temporary states, so atoms relax to their ground state by transferring their excess energy to other atoms or molecules present in the medium. Now we are going to see the sample introduction system, means how sample is introduced into the system. So atomization devices fall into 2 classes. So all of the atomizers I mentioned earlier in the table, they can be put into 2 classes: continuous atomizers and discrete atomizers. Now see, what are these? With continuous atomizers, and what are these atomizers? Plasma and flames, these fall in continuous type of atomizers. So in these atomizers, we have to introduce sample in a steady continuous stream. So we have to introduce our sample in a continuous form in these type of atomizers. While in discrete atomizers, samples are injected in a fixed volume, and that is done by the means of a syringe or autosampler. So you can see here is the syringe and here is the autosampler. You are well aware of the syringe, and autosampler means all of your samples you can put here in this device, and you give command to your system by the use of software, and your system that picks up all of your sample one by one. And the most common discrete atomizer is the electrothermal atomizer. Now sample has been introduced into the system. Next step is the nebulization. So sample is first nebulized before entering into plasma and flame, because we know that most of the time our sample is in solution form. So nebulization is a must process which must have to be performed. And what is nebulization? So to nebulize means to convert a liquid into fine spray or mist, means the larger droplets, they are converted into fine spray or mist, and this process is called nebulization. And this is done by the use of nebulizer. So nebulizer, it constantly introduces the sample in the form of a fine spray or droplets, and this is called aerosol. Now what is aerosol? Aerosol, it is actually a suspension of a finely divided liquid or solid particles in a gas. So mixture of those finely divided particles in a gas, that is called aerosol. Now when a sample is introduced into a flame or plasma continuously, a steady state population of atoms, molecules and ions develop. I will explain it right now in the figure given below. When we use the discrete solution samples, so samples are introduced by transference and alicate of the samples to the atomizer. Means a fixed amount of sample is introduced in atomizer, as I mentioned earlier. And here is the whole process which is described in this diagram. You can see here is the sample solution. Next step is the nebulization. So we use a nebulizer which convert this sample solution into fine spray. So this fine spray, this is mixed with air. So this is also known as aerosol. In this form, it is entered into atomizer, which may be flame or plasma. Now this aerosol, this has been entered into the atomizer. So by using the heat from atomizer, the first step is desolvation. So solvent is removed, and now this aerosol that is converted into dry aerosol. The next step is by gaining further heat from the atomizer, there is the volatilization phenomena. Means our sample, or what do you say, the components, they are converted into free atoms. There might be further phenomena. These atoms may rejoin together to give molecules, and further by getting heat, they might be decomposed again into free atoms, or these atoms may get sufficient energy which is equal to their ionization energy, so they may remove one or more electron and they may be converted into ions, and these ions, by getting the electrons back, they might be converted into free atoms. And remember, in atomic spectroscopy, we are interested in these free atoms only. Now we will see how solid samples are introduced into atomizers. So solid samples are introduced by firstly vaporizing them, and this can be done by the use of an electric spark or by a laser beam. Laser volatilization means by the use of laser. This method is also called laser ablation, and it has become popular method for introducing samples, for introducing solid samples into inductively coupled plasmas. And what happens in laser ablation? In laser ablation, a high-powered laser beam, often which is NdYAG, which is pronounced as neodymium dot yttrium aluminium garnet, or excimer laser, which is a UV based laser. So these lasers are being used in this phenomena, and these are directed onto the portion of the solid sample. In this way, the sample is vaporized by radiative heating from this laser device, and the plume of the vapors produced, these are swept into plasma by the use of some carrier gas, which may be air. Dear students, in this video we are going to discuss flame atomizer in detail. A flame atomizer, it consists of a pneumatic nebulizer. Pneumatic nebulizers are those nebulizers which use gas. A pressurized gas is used to convert the liquid sample into fine droplets. So it converts the sample solution into mist or aerosol that is then introduced into burner. And there are different designs of pneumatic nebulizers, and one of the design is shown over here, and that is the concentric nebulizer, which is most popular. So you can see here is the concentric nebulizer, and why it's called concentric nebulizer, because there are two tubes. This is the inner one and here is the outer tube, and these are concentric to each other. Through the inner tube there passes sample, while in the outer tube there passes the argon gas. And by the use of this argon gas, the pressure of this gas that is used to convert the sample, and that is converted here into fine droplets. Now we talk about the burners which are used in this flame atomizer. So two types of burners are mostly used, most popular, and these are total consumption burner and premixed chamber burner. While this later one that is mostly used, and that is premixed chamber burner. But we are going to see both of these. So let's see total consumption burner first. Here's the diagram of total consumption burner. In total consumption burner, the sample solution, the fuel, and the oxidizing gas, these are carried through separate passages and meet at the opening of the base of the flame. So you can see here is the sample passages, here is the fuel passage, you can see here, and here's the oxidant passage. So all of these three components, they pass separately and they meet at the base of this flame. And all the quantity of sample that reaches flame, so that is why it is called total consumption burner. So next design is the premix chamber burner. It is mostly used in commercial instruments, so it's a popular one. It is also known as laminar flow burner. And what happens in it? The fuel and support gases, these are mixed in a chamber before they enter the burner. So we can see here is the diagram. Here is coming the fuel and oxidant, and before entering into the flame, both of these components, fuel and oxidants, these are mixed in a chamber. Here is a chamber, so there is a pre-mixing of these components. So that is why this one is called premix chamber burner. Sample solution is aspirated through a capillary by Venturi effect using support gas. So you can see here's the sample and here's the sample capillary. So sample is drawn up through this capillary by use of Venturi effect. And what is Venturi effect? That is the support gas, which is normally air, that creates partial vacuum at the end of capillary. So partial vacuum is generated at the end of this capillary, due to which sample is drawn up in the capillary. And next part, we know that there is a nebulizer, so this sample is broken into fine spray. So here is the phenomena of nebulization. So all of these components, fuel, oxidants, and sample, that is mixed well into this chamber before they enter into the burner. After nebulization, the sample is converted into fine droplets of varying sizes. So the larger drops, they condense and drain out of the chamber, which is shown in the previous figure. The remaining drops, and these are fine droplets. So only these droplets mix with the combustion gases, and then these enter into the flame. It has been estimated that only 5 to 10% of the sample enter the flame, which is sufficient for producing the result, for giving you information about your sample. Combustion with premix burner is quiet. It is very much quiet. So this is the advantage of this burner, because previous one, that is total consumption burner, that is very much noisy. And a popular version of this premix chamber burner is boiling burner, which is shown over here. This is the boiling burner. And this boiling burner, this is a 3-slot burner. You can see here are the 3 slots which are clear. You can see here, resulting broader flame. So that is why the flame generated, that is quite broader. And because there are radiations coming from the radiation source, and they must have to pass through the flame. So when flame is broader, so there are lesser chances of distortion of these radiations. Now we'll see the properties of flames. So here is the flame, and it is divided into different regions. Let this be the primary combustion zone. Here's the second zone, which is called interzonal region, and this is the outermost region. This is called secondary combustion zone. So when nebulized sample is carried into a flame, the droplets are desolvated into primary combustion zone. So here sample enters into the flame, and it enters into the first zone, which is the primary combustion zone. And what happens here? Sample is desolvated, mean solvent is removed. The resulting finely divided solid particles, so these are carried into the next zone, which is present in the center of the flame, and this is called inner cone or interzonal region. So now sample is entered into this region, and this is the hottest part of the flame. And here the particles are vaporized and converted into gaseous atoms, elementary ions, and molecular species. So the atomization phenomena that is completed over here. And if we are discussing the atomic emission spectroscopy, so emission phenomena also occurs here. And then finally, the atoms, molecules, and ions, these enter into the outermost region, which is called outer cone or secondary combustion zone. And here oxidation may occur before the atomization product disperses into the atmosphere. So the sample is oxidized and then it is dispersed into atmosphere. And unfortunately, flame is not a very much efficient atomizer as compared to the plasma atomizer, and that is due to its lower temperature range. Now we will discuss the types of flames. So flame can be generated by the use of fuel and oxidant, and here are different compositions of fuel and oxidant. So oxidants here are shown only 3. They are air, oxygen, and nitrous oxide. So let's see where the oxidant is air. So the composition is gas here, means the fuel is gas, and gas used, that is maybe propane or natural gas. So when the composition is gas air, the temperature is 1700 to 1900 of the flame. Another composition is hydrogen air. Temperature is 2000 to 2100. Another composition is acetylene air, and the temperature of the flame is 2100 to 2400. So that overall temperature range when the oxidant is air, that is 1700 to 2400 degrees centigrade. And at these temperatures, only easily excitable species like alkali metals and alkaline earth metals, so they can be, studied by using these type of flames. But if we are studying the heavy metals or those elements which are not easily excitable, so we must have to change our oxidant. So we can use oxygen or nitrous oxide. So let's see what is the temperature ranges. So when we use gas oxygen, the temperature range is 27 to 2800. Then hydrogen oxygen temperature is 25 to 2700. And for acetylene oxygen, the range is 3050 to 3150 degrees centigrade. And same if we see the acetylene nitrous oxide, the range is 2600 to 2800. Means the overall range of these flames is 2500 to 3100 degrees centigrade. So that is, the temperature is high. So by using these flames in which the oxidant is oxygen, so we can study even those species which are not easily excitable. Now we will see the atomic absorption spectrometry, AAS. Flame atomic absorption spectroscopy is currently the most widely used of all the atomic spectroscopic methods. And this is due to its simplicity, effectiveness, and a relatively low cost. This technique was introduced in 1955 by Walsh in Australia and by Alchemade and Millatz in Holland. The first commercial atomic absorption spectrometer was introduced in 1959, and then this technique grew explosively. So let's discuss the instrumentation now. So here is the block diagram of single beam atomic absorption spectrometer. So first one, there is a line source which produces lines. These lines are directed to the atomizer where sample is present in the form of gaseous atoms, and here is the absorption phenomena, and these radiations are then sent to the monochromator, which is set on the radiations of our interest. It converts polychromatic light into monochromatic light, and that then there is a detector, which is photomultiply tube, then there is signal processor, and finally we get our result on the screen of computer. And here is the schematic diagram of double beam instrument. The first component is same. You can see the hollow cathode lamp which produce radiations, and these radiations are separated into two equal beams by using of this chopper. One beam act as sample beam while other acts as a reference beam. So this sample beam, this passes through the burner through the atomizer where gaseous atoms are present, and here is the absorption phenomena, and rest of the instrumentation is same. There is monochromator, there is detector, and then there is a computer system. Dear students, you can see the details of the parts like of optical chopper, monochromator, and detector. So you can see the details of these parts into my another video, that is the instrumentation of UV visible spectroscopy. So I am putting the link of that in my description. So here we are going to discuss the line sources only. So first of all, we are going to see the hollow cathode lamp. The most useful radiation source for atomic absorption spectroscopy is the hollow cathode lamp, and it looked like this one. It consists of a tungsten anode and a cylindrical cathode. You can see the anode, which is made up of tungsten, and a cylindrical cathode, and these are sealed into a glass tube. So here these are sealed, both of these are sealed into this glass tube, and this tube that contains an inert gas, neon or argon, that has been filled inside at the pressure of 1 to 5 torr. The cathode is either made up of that element which you are going to analyze in your sample, or whether it provides a support, means the compound of that element that is coated on this cathode. So whether cathode is made up of that element or it supports the compound of that element. So if a potential difference of 300 volt is applied across the electrodes, the argon gas present inside that ionizes, mean argon that is converted into argon cation, and there are free electrons. So both of these charges, they move towards their respective electrodes. So electrons move towards anode and argon cations move towards cathode. And this movement of charges, it generates current of 5 to 10 milliampere. And if the potential is large enough, the cations strike the cathode with a sufficient energy and dislodge some of the metal atoms to produce an atomic cloud. And this process is called sputtering. And some of the sputtered metal atoms now, they are in their excited state, which is the transient state. So soon they return to their ground state by emission of radiations. And these radiations, these lines are used to be absorbed by the sample present in atomizer. The sputtered metal atoms eventually diffuse back to the cathode surface or to the wall of the lamp and are deposited there. So in this way, this lamp can be used again and again. Hollow cathode lamps for about 70 elements are available commercially. Some hollow cathode lamps, they use cathode that is made up of alloys, mean that is a mixture of different elements. So it will generate spectral lines for all of those elements. Another design of line source is electrodeless discharge lamp, which is shown over here. These are useful sources of atomic line spectra, and these lamps are often 1 to 2 order of magnitude more intense than their hollow cathode counterparts. Means these lamps produce radiations which are more intense as compared to hollow cathode lamps. A typical electrodeless discharge lamp is constructed from sealed quartz tube. You can see here is the sealed quartz tube, and it also contains an inert gas like argon. So argon gas is present inside at a pressure of few torr, and a small quantity of the analyte metal that is put inside this tube. The lamp contains no electrodes, that is why this is called electrodeless discharge lamp. So the analyte metal that is energized by an intense field of radio frequency or microwave radiation. So here is the RF coil, you can see. So again, argon ionizes here in this field, and these ions are accelerated by high frequency component of the field until they gain sufficient energy to excite, and they collide by the analyte atom present inside, and what do you say, they are energized to their excited state, and when they are returned back they produce lines. Electrodeless discharge lamps are particularly useful for elements like arsenic, selenium and tellurium, because these require intense lines as compared to the other elements, and these intense lines are not produced in case of hollow cathode lamps. So dear students, this is all about atomic absorption spectroscopy. Like my video, and if you didn't subscribe my channel yet, then subscribe it right now to get more interesting videos. So thanks for watching. Thank you very much.